Welcome back, everybody. Welcome back to the channel. So today we're going to be talking about how to build an exception system. It's going to be a little bit more of an advanced video, so keep that in mind. Also, I'm going to try to keep this video short. Exceptions are a pretty complex topic, so let's just kind of get right into it. So we're going to start out right here with the high level portion. Now, one thing before we get into this, I will say you cannot build the exception system unless you have both the high level and the low level down pat. So first we're going to start by obviously throwing a new error. And error is just an alias for an exception, and let's just say error, right? Now, if we just do this without catching it, we can actually see what the source code is going to look like. So I'm going to open up the compiler here. And I'm also going to go to the source code. So while this code is compiling, put that down. If I go to the actual exception source code, we're going to be going through all this. So the first thing I want to do is create your exception hierarchy. Now, we're not going to go into the source code right now. This code is mostly based off of how Java handles exceptions. It's a very efficient way of handling exceptions, so we'll go over that in a second. But you want to have at the start what's called a base exception class. A base exception class is going to represent the lowest level for exceptions in our programming language. So just like how every class inherits the object class in my programming language, if I go to here, just like every class inherits this, every exception must inherit the lowest level version of an exception, which in my case is a throwable. And above that, there is a class called an exception, which represents a high level version of a throwable. And I have my basic constructors here. And then after that, I have just all of my base level exceptions, which all inherit the exception class. So that's going to be the basic hierarchy. So at the start, you're going to want to create that basic hierarchy to kind of give your exceptions some structure. And then you can start to do fancy stuff like, for instance, I created a bunch of type aliases. As you can see, error is a type alias of exception. And I created some functions here, which doesn't really matter. I mean, you guys can create these if you want. These are just very quick ways of throwing exceptions. So if we go back up to the actual source code, looks like the code actually compiled. Yeah. So now I'm going to go to the syntax and I'm going to split this vertically. So that way we can look at this side by side and I can go back to the actual syntax code. Why is it flipped? That's weird. So I'm gonna split this one. We can actually see what is going on. We can actually see if we go to the main function. Where's that? That's not it. Okay. So in the main function, all we do is we create a new class of exception. We duplicate it, which I mean that's just stuff that's generated by the compiler. We create the new string of error. We call the std exception function, and then we take that object and we actually throw that object. So this is the basic code generation for an exception. And if we actually go to the low level, now let's actually see what is going on at the low level when that actually happens. So if I go to thread here, and if I do a search for throw, right, once we actually throw the exception, we're going to just pop the exception off the stack. And remember, we did duplicate the class, so we have two copies of this exception class to actually access and manipulate. And we send the signal of 1 for an exception, and we jump to exception catch. Now, here's where we actually handle exceptions. So if you remember, all of my source code is surrounded in a try catch. So that means that if we get an exception, we will send the signal and then handle the exception down here. Now, before we go into the actual source code to look to see how we actually catch an exception, let's look at the basic premise of how I actually handle catching exceptions. What we do is we have this exception catch here, and we first want to check to see if the state is killed. That is entirely possible that at the point during the catching of an exception, we could be killed in the process. So if that's the case, we just send a signal of tsig except just for good measure. and we return. After that, we have a pretty simple system when it comes to handling exceptions. I try to catch it. If we couldn't catch it, I try to return. And if return returns true, that means that we're either inside of a JIT function now that we need to return our scope back to, or we need to return our scope back to native C++ code. So if that's the case, I return. And if you guys remember, it's not going to go to it now, but if you guys remember in the return method function, it will return true or false based on whether or not it's either A, the last function that we have called, or B, it is a JIT function. Now, after we return the method, we want to increment the PC. We do this after the fact because now we've updated the PC to where it needs to be so we can continue executing source code. And if we did not catch the exception, or since we did not catch it here, by the time we jump back up to the top, we will handle this exception again because if you guys remember, BRH actually does the check for whether or not we have an exception signal. So it's going to happen immediately on the very next instruction. Now, even if we catch an exception, we still may need to return back to the JIT or the C++ source code. So we check to see if the current function that we're executing is in fact a JIT function. And if so, we return out of this scope back to the lower level. After that, if that's not the case, then we go to run, which just basically jumps back up to the top of our for loop and goes down here and dispatches to the next instruction. So that's kind of the basic way on how we actually handle exceptions. Now, let's go back to the high level to observe what we're actually doing with the exception system and the support library. So if I go back to the support library, you can see here that I have this throwable class. So for my exceptions, I have the message field and a stack trace. Pretty standard, right? You want to have a message for what you're actually telling the user that went wrong. And then you also want to have a stack trace, which represents, of course, the stack trace of, your functions that led up to the crash. Now, there's a huge problem when it comes to a stack trace. Stack traces can be huge, and now with my language, I have limited my stack trace to a total of 20 functions, meaning that you're going to get stack trace of up to 20 functions leading up to the actual crash. So that means that there's a potential that we could have functions chopped off at the very beginning if we have a huge chain of function calls where something led up to the actual crash. Now, when it comes to the stack trace, I check to see if the stack trace is equal to null. If so, I set the stack trace equal to the stack trace from the virtual machine. So initially, whenever you throw an exception, we don't want to just build the stack trace because that's a waste of energy. We want to build what's called a frame info. And Java does the exact same thing. This is straight out of the Java virtual machine. Java does the exact same thing. So if I go to platform kernel, you can see that we have this data called stack state. And a stack state, all it represents is the state of the stack during the current point execution. So the stack state is going to represent the list of methods that have been called and the program counter that we're at during the current execution. So as we basically call each function, we're going to call function foo. That's going to be locked at, I don't know, PC of 10. Then we're going to call another function, maybe called add. So if we call add, and that function PC is going to be locked at 37 or whatever, right? And it's just going to keep going on. So we'll be able to get an actual view of each of these. So there's that. So if we go back to exceptions, basically we want to, whenever this class is created, I have an init block, which basically sets up the frame info by saying vm.getFrameInfo. So whenever we create an exception and pass in like the message or whatever, then this will subsequently create the frame info. And in fact, this actually speeds up the exception system by a crap ton because you're not having to build that entire string. And if you're throwing thousands of exceptions, now again, I know this is a edge case, but if you're throwing thousands of exceptions, it could actually slow things down quite a bit. So us doing it this way allows you to throw several thousand exceptions without having much issue in terms of performance. So let's actually go a little bit deeper to see what getFrameInfo is. So getFrameInfo is created in the virtual machine and it's right here. So I have two functions. I have getFrameInfo and getStackTrace. Now getFrameInfo is just going to basically call this system interrupt and it's just going to return the data. GetStackTrace is going to take in a stack state, push that data on, call this system interrupt, and then return the data as well. So if I go to the virtual machine, we can actually see if I cancel this and actually compile the virtual machine, oops, you can see what the code looks like. So we're going to need to mirror both of these values at the low level in the same way that we do at the high level. So if I scroll up to the top, we can see we have two of the very similar functions. We have getFrameInfo. It's going to take an object of FrameInfo, then getStackTrace, which just returns void. So getFrameInfo, if we look at this one, so what we do to actually get the frame info is we make sure that the call stack is not equal to null. If it is, we return. After that, we check to see if the frame info object is not equal to null. And then we set the frame info object to a new object of stack state. Now, stack state is going to be an actual class that we will be pulling when we actually create the virtual machine. And we are going to set the methods in PC list field. Now, because I know where the fields are, I just say frame info and I access the node at the specific index. However, if the user were to go into the source code and actually modify the actual stack state, this could pose a problem. So keep that in mind. I would actually try to find the fields instead. So I could say vm.resolve resolve field, and that would probably be the best way to do it. And we've already gone over that function, so I actually don't need to do that. But once you get those two fields, then we're going to actually build the list. So what I do is I set the size of the total amount of functions that we're going to actually process equal to the thread.calls plus 1, because remember the thread.calls value is 0 based, so we need to plus get it 1 value to get the total amount of calls. We check to see if that is less than the print max. Then if it is, then I actually go for the total amount of calls. Otherwise, I say exception print max plus 1. Exception print max is going to be 20. So I'm actually going to be printing 21, it looks like. So then we create the actual objects for each field. So each of these objects need to be the exact same size. We cannot have them be out of sync with each other because obviously the same amount of methods that we have are going to be the same amount of PCs that we're going to have for the list. And if the methods are less than the total max limit, which is 20, then we just do for I is equal to 1, then I is less than or equal to the calls. Now, the reason why I say I is equal to 1 is because it's based off of the last function. Each time we create a new frame, we're going to be passing in the last function that were processed. So we want to actually get that data. So we want to go forward 1 just to make sure. I do a check to see if the I is greater than or equal to the exception print max. And if so, then I break. Now, the reason why I'm doing this, I know it seems silly, but we're going to be going for the total amount of calls. So let's say we have two functions. We have main, right? So if I do this, so if we have main and then we have foo. So if we have both of these functions, calls at this point is going to be equal to 1. It's not going to be equal to 2. Now, this might seem silly, but the reason why we want to do that is because we want to skip the last function because it's going to be not accurate information. So we want to get the last data by actually accessing the current function's address in PC, because if we go one more, we're not actually going to be getting the current function because it's going to be some undefined value of some random function that we called a long time ago. So for methods, we just set head, which is the numeric value at whatever the iter is, and iter is going to be this value plus plus. We use iter because it starts at 0 and I starts at 1. Then we say thread at call stack at I, and we get the return address, and then we access the address here. Then we set PC list based on whatever the PC was at that call stack as well. After that, we have the case where we have too many function calls and we need to pick the last 20. So what I do is I start at I, and then I say call I is equal to thread.call plus 1 minus exception print max. And then I say I is less than or equal to calls, and I say I plus plus. We do the same thing we did above, And then finally, we want to assign the last value in iter to the current address of the current function and the current PC of the actual current function. And once we do that, that's basically how we get frame info. Now, we're going to need to also look to see how we get the stack trace. Now, getting the stack trace is a little bit different. So what we do is we're going to get the frame info by getting the current object on the stack. And then we're going to say frame info, we're going to increase the ref count. And notice here that I'm getting the sharp object and not the object pointer, right? So notice I'm not getting a reference to the actual object pointer because we're going to need to update that object pointer. This get stack trace function is going to be putting a item of string onto the stack. So we want to actually get the original sharp object to hold, and we're going to simulate us actually holding this object inside of another container by incrementing the ref count and decrementing it once we're done and we're outside of this function. And as you can see here, we're setting the current item on the stack equal to a new string class, so that way we can actually contain the data. We fill the stack trace by passing in the frame info object and the current string class that we're going to be assigning the data to. So fill stack trace, what it does is it gets a couple of different things. We access the field of methods inside the frame info. We access the field of PC also inside the frame info class, which we've already seen. And then we access the data field, which is going to be represented in the string class. So we're going to want to access this field here. Once we do that, we'll go back to the virtual machine. We want to make sure that all of those are non-null, obviously, because if we find that actual field, we want to make sure that we have access to it. And if we do, then we call fill stack trace on all three of these objects. So then we pass into this function all of those fields, and we check to see again if the objects and values are equal to what they are. Now, obviously they're non-null. We also want to make sure that the objects that they contain are also non-null and that the types are exactly what they're supposed to be. So we want to make sure that the methods field is a var type, the PC list is also a var type, and that we have the data field. Once we do that, then we're going to create a native string and a string stream, and we're going to go through the entire list of the methods list, right? So we're going to go through the entire methods list, and we're going to call a function called a fill method call. So we're going to pass in the actual address of the actual method that we're trying to call, and we're going to percent it to the actual total amount of methods that we have available. This ensures that we don't go out of the index of this methods field. So we're actually going to be passing in the pointer of that actual function. We're going to need to pass in the program counter that we're at the current time of calling that function, and a reference to the string object. After we fill the method call, we set the actual string equal to the string of the string stream, and then we create a string array based off of this native string here, and we free that value. And when we create that string array, we use the data field, which is going to represent, again, this field, to then set that string value. So hopefully all that made sense. And then when it comes time to fill the method call, what we do is we set the source, and we're going to see an actual exception shortly. So I'm actually going to play an exception for you guys so you can actually see what it looks like. We're going to say function source file is not equal to -1, and the source file is less than the total amount of source files. We're actually going to print out the name of the source file by accessing the metadata files and getting the source file based off of whatever that function's source file address is pointing to. Now, it's entirely possible that we just don't know the source file, so we just want to make sure that that is the case. Otherwise, we're going to just say unknown file if we don't have access to the source file. After that, we for loop through the entire line table. So I create a couple of variables here, and I for loop through the line table. And what you want to do in this for loop is you want to try to find where the actual PC lined up with the current line of the actual exception. Meaning that you're basically looking here. So as you can see in this sn printf function, I have a couple different lines. All you're trying to figure out is where is the PC inside of these lines. So if this was the actual thing that caused the exception, it's going to be at line 4 because it's greater than or equal to the start of line 4 and less than the next line, which is line 13, meaning that it happened on line 4, if that makes any sense. So that's what we're doing there. And if pointer is not equal to null, which is actually pointing to the index of where we need to access the line table, we set the line equal to the actual line number in that line table. Otherwise, we say line is equal to question mark, which is entirely possible if, for instance, we're calling like a C++ function. Then we say in, we print out the full name of the function. It's very important to put the full name. You put a parentheses and whether or not it is a native function based on whether or not it is inside of C++. Now this native function boolean is going to be set if we are determined to have this be a native function determined by the compiler. So this is set actually when we're processing the executable, so this will already be true or false. We close the parentheses and then we have a debug check here as well. So if debug mode is enabled, which is a debug flag for the actual virtual machine, I print out a little bit more information to actually help me find the exception. I print out the actual function address with the left brace, the function address in the right brace, and I can just literally copy that and do a search for that in here. So that's why I have that format. And then I have $ in PC, which is what program counter did the actual exception happen on. Because it's one thing to know what line it happened on. It's another when you're building a virtual machine, you want to know precisely what instruction broke the actual programming language. So that's that. And then finally, we set the line by getting a pretty error line based off of the line, the source file that we passed in, and that's the end of the exception. So for pretty airlines, all you're trying to do is just print out a very nice way of showing the user where the actual error happened. So we're going to put 2 lines before the error and 2 lines after the error to give the user a decent view of where the actual exception happened. Now this is only going to work if we have debugging information enabled. So I'm going to check to see if the line is greater than 0. Then if so, we're going to add a new line, a tab, then we're going to say line, then colon, and then we're going to actually print out the line data. So we're going to get the actual line from the metadata and, for instance, print out something like this with the line directly in front of it, kind of like how I have line colon here and then some data. And then we do that for the second one as well. So we ++ line, and we again check to see if the line is greater than 0. If so, we print out the line. Now notice I'm decrementing the line by 2 values. So if we've determined that it happened at line 4, I'm going to print line 3 and 2 above it, and then line 13 and whatever below it. So as you can see, after we do that, then we do the exact same thing. So we just print out the actual line of where it happened. We print a new line, a tab line, colon, and then the actual data. Increment line and do the same thing 2 more times. Now, let's actually see how an exception actually looks in the programming language. So if I run the source code, and while that's compiling, we can actually go back to the high level, and we can see here that I'm throwing an exception that's not being caught. So it's literally just going to print out what actually happened. So we can see here, if we look, we have a full stack trace of the actual exception. So we say unhandled exception on thread, whatever, and in this case, it's the main thread, most recent call last, and we can see the stack trace that led up to it. And because I have debugging enabled, we have this information as well, which is the address of the function as well as the PC that actually crashed it. And now here's where it gets into information that is relevant to the actual crash and non-relevant information. If I go here, you guys can see that here's an exception example from Google where if you get like a null pointer exception, now this is an Android exception. You don't really need to know what's going on here if you haven't programmed in Android. I just want to point something very important out. We can see here that these values are blue and these values are gray. What that means is that these are non or less important information about what led up to the actual exception. So these are going to be files and functions that led up to the actual exception that aren't part of the user's source code. So in our example, we have that information as well. We have here, the user didn't create this platform SRT init. This is the starting point of our actual main method. Then we have the main method, which is the actual user source code that actually threw the exception. And then we have some other code, which is a part of the exception system that actually pulled the frame info. And again, these are going to be values that aren't really relevant to the actual user. So keep that in mind when you start seeing your exceptions. You want to make sure that you don't have too much noise in regards to your exception systems. So for mine, I don't really call that many functions in order to access the frame info, so it does not create that much noise because it's going to actually take away every time you call an exception 3 functions that the user could have potentially seen before the actual exception was thrown. So if that makes sense, keep that in mind. You can see here that I have the exception of error. And yeah, so it took about 400 milliseconds, which doesn't matter. It's just a little slow because I'm running in debug mode. So that's how we actually throw an exception. Now let's look at how we actually catch an exception. Now this part is going to be the meat and potatoes of the actual lesson here. So if I try to throw this exception and then I catch the exception error, we're going to actually see how all of this stuff ties together. So if I go back to here, now here's something very important that I want to mention. My exception system used to rely on the low level to actually do all of the control flow logic for the actual exception handling. And I know we still haven't reviewed the catch exception function. We will be going over that shortly. However, when it comes time to throwing and catching exceptions, we want to have the high level do as much work as possible to make actually our programming language a lot faster when it comes to throwing exceptions. So if I go up here to the Sharp compiler and I try to compile the source code, we can see that there's going to be a little bit of a change. Now I want you guys to pay close attention to the start and end of the try catch. So we can see here, oh, it's actually not focused on the main function. So if I refine the main function, we can see that during the start and end of the actual exception, we have a try start and a try block start. We throw the actual exception, then I have a try block end and a try end. There's going to be 2 completely different concepts of the try catch block when it comes to throwing exceptions. A try start and end is going to represent the full range of the entire try catch block, and a try block start and end is going to represent just the try block. Now, it's very important that we do that because this allows us to, with this differentiation, always guarantee that we can execute finally blocks. As you guys remember, finally blocks are always guaranteed to execute in a programming language. So we're going to go over how finally blocks are handled shortly. But when we actually look at this, we can see here that when we throw it, if we ignore this for a second and assume that we're not actually throwing an exception, you can see that immediately after that we have code that's being generated where we're jumping to the try block in, which is known as address of 7. Now, because I have no information in here, my compiler actually generated some source code to fill in to the actual catch block so we can actually jump to something. So it just does nothing here. So it does no op. And if we assume that this doesn't actually throw an exception, in normal cases, what we're going to do is execute the code inside the try block and jump to the end of the try, which is going to be after the catch block. So we're going to jump down here, and that's going to represent no op, and that's it. And then we just return. Now for the catch block, we're again going to, after we execute everything, jump to the end of the actual try block, which is going to be after all of the catches, because if you remember, you can also chain catches. So if we have another error, error 2 or whatever, we can also chain together catches, so we still want to jump to the very end of that block. So that's why this no op was generated as a result. Now, if I put a finally block here, that's going to change things slightly. So let's say I put this finally block and I print, I don't know, hello, right? And even though I'm throwing an exception, we are guaranteed every time to actually execute this finally block. So if I run this again and recompile it, we should see this source code over here change shortly. Yeah. So now we have a little bit more source code. So if we look at this, we have all the same crap that we had before. The only difference is now you can see that I have a move local of 1 and I'm deleting that actual field. The reason why is because when it comes to finally blocks are very complicated. We'll go over this a little bit more later on. But I have a concept of a variable called unhandled exception. And that's going to be a, exception or an error in our case. And that's going to be either null or non-null. Now, if we threw an exception and we could not catch the actual exception, then we're going to immediately jump to this finally block, and we're going to actually set this unhandled exception to not null. The reason why is because, again, finally blocks are complicated, and we want to make sure that at the very end of executing our finally block, do a check to see, and I'm pretty sure Java does this as well. We check to see if unhandled, so if I go back, unhandled exception is not equal to null, and if so, then throw unhandled exception. Because we don't want to have this exception looming over our head while we're executing the code in the finally block. Now, what happens if you throw an exception inside the finally block? What's going to happen is we're going to ignore this unhandled exception and print out the new exception that is being thrown in the finally block. And now what happens if, this just gets really wild as you start to really get into exceptions. What happens if we try to catch the actual exception again, right? So if we try to catch this error, then if we throw it inside the finally block, then we're going to check to see, oh, we're inside of this block. Well, now we need to jump to any catches that this specific try block has. So we jump to this catch, and then we can execute the finally again. Or if we just have a finally, we will literally jump from this finally to trying to catch the exception, realizing that it doesn't have an exception to catch, then jump to this finally, and the exception that should be printed should be the newly thrown exception, not the unhandled exception, if that makes any sense. Exceptions are very disgusting. This is why I've been avoiding this video, but that's kind of how it works. And you can see it here in the code. So if I remove this, then you can see that I actually print out the new string of hello. I call the print function, which is here. And if I remove this code, this is just me showing what the compiler is actually doing. I'm doing literally what I just wrote. So I'm checking to see if that unhandled exception field is equal to null. If it is, then I jump over the value to 16, which is the end of the finally block, which is a no-op that's generated by the compiler. Otherwise, I push that unhandled exception onto the stack and I return with an error. Now, if you guys remember, if I go back to the actual multi-threading platform, if we return with an error, we actually put that, so if I go to RET, we actually put that error onto the exception object. So we pop that value off the stack and reassign exception object to then be handled by the exception system. So that's kind of the full look at what happens. And if I scroll down, or actually, you know what, I'm going to go here. So if I go to exception catch, now we're actually going to look at the catch exception. And once we do that, that's going to be pretty much the end of the video. And the final thing that I'm going to do is just do some wacky crap to show you guys how my exception system actually works. So if we open this up, we can see here that we create a bunch of variables and we want to access the handling class. Now I need to actually switch back to the virtual machine. We set the handling class by accessing the class's value inside of the info of the exception object. Now you need to make sure that you protect at the high level, at the compiler level, that you can only throw classes that are representing an exception class. So it either has to inherit the exception class or the throwable class for it to be a valid exception. And if I go back, so once we do that on the compiler side, then we're ready to do it on low level. So I for loop through the entire try catch table. I get the current try catch data, and I check to see where we are in the start and end of the block of the actual try catch. So what we're looking for is where are we in terms of this part. So if we're inside of this value here, then we want to try to search for any catches that may be after that value. So if I go back, so once we do that, we want to, the way I do the check is I make sure that the actual handling class's GUID, which is completely unique value, is equal to the actual caught exception on that actual try catch. And that means that we cannot do inheritance. So what this means is we cannot have a class called A, right? And A has a base of exception. Whoops, my caps lock went on. And then we can have a class of B have a base of A, right? And then we then subsequently go to throw B and then try to catch A. That it doesn't work that way. You can't do that. That doesn't make any sense. So what we want to do is we want to have the user catch the exact exception that they're throwing. We don't want to supply them with an easy way to just catch everything. Now, how does it work where if I throw, for instance, that class of B and then I catch an exception? Well, how does that work? Well, literally, I'm just doing that check here. So otherwise, if it's not exactly equal to the class, I check to see if the caught exception is in fact the exception class or the throwable class. If it's either of those values, that's just as valid as catching any exception. It's allowing us to have an umbrella to catch everything. And then after that, I set the local field address of the catch table. So what that does is if you guys have ever programmed in Java, as you know, you can say catch error, right? And then you can literally not include the field's value that you want to assign to, because if you wanted to include this, then you could print, e dot get message, right? Pretty sure you guys have seen that function in Java before. So because we actually don't need that field, then we can just do that, and that's going to tell the virtual machine that this local field address is less than 0 or -1, meaning that we don't have a field to actually assign for this specific caught exception. If we do, though, we basically access the local fields address object based on whatever the frame pointer is. So if you guys remember, this is going to be a local field that is on the current frame of this function, and it's going to have a specific address. So we literally just say frame pointer plus the address of this field, and that's how we access it to set its value. So once we do that, we set that equal to the exception object, and then we say PC is equal to the cache plus the handler PC. So basically all we're doing is we're starting or we're resetting the program counter equal to the start of this catch block. So we're going to be starting. Now, I know some of you are wondering, well, what happens if we have a JIT, right? Like, as you know, the JIT does not really operate on the program counter directly because it's just a bunch of generated assembly code. Well, what I do is if you're going to build this in your JIT, what you're going to want to do is once you get out of this function, inspect the PC, and you're literally just going to say go to JIT underscore labels, if you guys remember what that is, at PC, and that's it. Literally, and what that's going to do is, if you remember, we have this JIT labels field where it has a reference to all of the starting points of every single instruction, and it's going to allow us to have the same effect as we would at the high level as we're interpreting our virtual machine to jump to the exact source code at the start of the catch block. So once you do that, then you set the exception object to null because obviously the exception has been handled. We send the signal of 0 and return true, stating that we have caught the actual exception. Now, if this doesn't happen, we will have a fallback. So this is the fallback where we actually look for the finally block to actually execute in our source code. So what we do is we look to see if we're between the actual full range of the try-catch block. So if we're inside of this block, or any of these subsequent chained catch blocks and we throw an exception there, we need to execute the finally block, because even if we throw an exception inside of the catch block, we still need to execute this code. So we are checking to make sure that we're in the full range of this block. Now I know some of you are wondering, well, what happens if we have a try catch block here with a finally block, so we have like nested finallys. Which one are we going to execute? Well, the way that it works, if you really think about it from the compiler's perspective, if you notice, we're starting at index of 0. If I go here, as the compiler is compiling this code, it's going to add a list of try-catch data. So what it's going to do is it's going to start here, and it's not going to actually add the try-catch data. First, it needs to compile the source code inside of the try-catch block. So once it's compiling the data in the try block, it's going to then encounter this, which is going to then subsequently add its value and the finally block and all the information inside of the try-catch table. So in fact, the fact that you're starting from 0 means that you're starting from the innermost value all the way back up, because that's how it works from the compiler's perspective. So that's why it's safe for us to do this. So that way we know precisely where we are and what we need to execute in the try catch block. So once we figure out where we are in the full range of the try block, we check to see if that specific try block or that specific try table has a finally block attached to it. And if the finally block is not equal to null, then we set the PC equal to the starting point of that finally block. We assign the exception object field address or the unhandled exception object equal to the exception object field, and then we set the exception equal to 0. Now, this basically shows that we're handling that actual exception, and that's it. And in fact, I actually think I forgot to do this. You also want to set the exception object equal to null, but you want to make sure you do it after you set the field. So after you set the field, set the exception object to null, because as far as we're concerned, the exception has been handled. And the only way that we're going to rethrow the exception is because the high level or the compiler generated code told us to, because we have this check to make sure that that field is not equal to null. Now, again, if we go back here, if we actually throw an exception inside of the finally block, we're going to do all this source code again where we're checking to see where we are in the try block, and we're going to look to see if we can catch any of those exceptions. If not, we look for the full range of the try block and then check to see if that has in fact a finally attached to it. So that is the full stupid and complicated exception system. Now let's actually see what actually happens. So I'm going to say print caught me, and we can catch the exception, and I'm going to also print the finally 1, and then we can also print the finally 2 as well, and we can see now what do you guys think will happen. So obviously we're throwing an error. Obviously what should happen is we should catch it and execute both of these finallys. So if I go back to the compiler, I'm going to recompile this source code, and we can see what the generated result would be. Now, the source code that's going to be generated here is going to be a little bit different because we do have to, I also have a concept of finally chaining, which is a whole nother can of worms that I don't even want to get into. Basically, finally chaining is a concept where we chain together, executing a bunch of finally blocks at the high level. Yeah, we'll go over that later. I don't want to confuse you guys anymore. So if I go back to here, you can actually run the code and see what happens. So let's go back to the syntax file and run it. So this code should actually, just like I said, print out the caught me and both finallys. Now, while that's running, I'm actually, oh, my computer froze. I'm actually going to remove this catch block. So we're just going to show the finally, and then we can actually see what happened. So we say caught me, and I didn't do a print line there, but caught me, finally 1, finally 2. Now we should get literally the exact same result if I throw the exception and I try to run these two finallys. I should still get the printout for both of those, and we can actually see the source code that's generated really quick to understand why that's happening. So we throw the exception, and that code is on line 10. So we actually throw the exception. And now, assuming that nothing happened, we jump to the end of this block, which is going to be the start of the finally. So we're jumping to 6. We set the value equal to null. Now, because we're actually throwing it, what's going to happen is we're going to throw it, and then we're going to jump to this part, which is the start of the finally. And the value is going to be set to the actual exception of error. And we're going to then subsequently print out finally of 1, check to see that it's not equal to null. And now we're going to do something different, which again is called finally chaining. It's a very stupid thing that there's no other way that I could have done it. So this is what I do. I basically try to jump to 14, which jumps over this source code to the end of the finally block, and then it'll just execute this source code. But since it's not going to be equal to null, we're going to execute this source code, which jumps to 18, which literally jumps down to the next value of the next finally block, again, finally chaining. We're going to then print out this value and then again check to see if the value is equal to null. And since it's not equal to null, we're going to push the object and return with an error. So all of this source code is literally being generated by the compiler, and it's Yeah, it's pretty crazy. So if we run this code, you can see that we'll get literally the exact same result. And we get an exception error. However, look at that. Finally one, finally two. So we still have executed both finally blocks, despite the fact that I threw this exception inside of a doubly nested try catch block and a doubly nested finally block. So that's kind of how the system works. And this again guarantees that finally blocks will always be executed. And because it's an unhandled exception, we will in fact get the actual exception here. Now, if I caught the exception here, we'll just, catch the exception and again, still execute both of these finally blocks. So that's kind of how the system works. Hope I explained this to the best of my ability. If you guys have any questions, definitely don't feel shy to put it in the comment section below. I know this is a really advanced video. So that's going to be it for today. As usual, if you guys would love to help support the channel, as always, you can head over to the GitHub repository at andrewdevcd/sharp. And when you do, definitely watch, star, and fork this repository. That gives this language a lot more visibility and let other developers know this language exists. Also, if you guys are curious about some of the things that I've been up to recently or some things that I'm looking to add in the future, you can head over to the roadmap file. This is a very nice high-level way to view all the various different things that I'm looking to add in the future to the programming language. So that's going to be it for today, guys. As usual, if you're new to the channel, definitely consider subscribing, and until next time, I'll see you guys later.